Hi everyone, rapid review of the problem we ended with. So we talked about two different ways of thinking about multiplying complex numbers. If I've got a number a, which is a plus bi, and b, which is c plus di, you could multiply them out this way and then collect the real parts and the imaginary parts. And because that's the rectangular way of thinking about complex numbers, you'd be able to plot how far over and how far up do I need to go in order to find this value c, the product of a and b. We'd also discussed a geometric rule. When you multiply two complex numbers, the angles add to give you the angle to the product, and the magnitudes, the distances to the origin, multiply to give you the magnitude of the product. We use this geometric way of thinking to try and find the roots of equations like this, x cubed minus 1 equals 0. If I add 1 to both sides and then expand x cubed as x times x times x, I've got that some complex value x times itself 3 times should equal 1. So we already know that x equals 1 is a solution to that equation. And we're trying to find other values. So imagine that this is the real axis, this is the imaginary axis. We're imagining some value for x. Maybe it's here, maybe it's somewhere else. And we want to imagine geometrically what happens when we cube this number. Well, we know that the magnitude is going to end up the cube of the original magnitude. So because we need the magnitude to end up at 1, because that distance is 1, it seems that the magnitude of x has to equal 1, because it's the only number you can cube and have it remain as 1. For the angle, we know that cubing x is going to add the angle to x to itself 3 times. And we know that if x cubed is supposed to end up being the same as 1, if we add the angle 3 times, it needs to end coterminal to the angle that leads to 1. In other words, the angle 0, or 360, or 720. So we can get the angle that way. We can say the angle to x is the same as 360 degrees over 3, or a different angle to x could be 720 degrees over 3. Which would be 120 degrees or 240 degrees. So this picture actually isn't accurate at all. This can't possibly be the value for x, because if we added this angle 3 times, we'd end up kind of over here. So let's cross that out. So here we have the actual roots of that equation. We've got one value is 1 itself. Then we've got this value, which if we're expressing it in a polar way is an angle of 120 degrees with a magnitude of 1. And this is an angle of 240 degrees with a magnitude of 1. Okay, well, what if we want to rewrite these in rectangular form? So you can use, excuse me, you can use SOHCAHTOA, or you could realize that it's really the same thing. This is on a unit circle because the distance is 1. So the cosine of 120 degrees should give us that x value. The sine of 120 degrees should give us that y value. So because 120 degrees is the same thing as 2 pi over 3, we've got cosine of 2 pi over 3 is the real part, and then the imaginary part is the sine of 2 pi over 3. And then hopefully you remember some of these values. We're going to be really drilling these next unit. But this cosine value would be negative 1/2, and this is root 3 over 2. So that is one of the two roots. The other root, I don't know if you can tell, but it's symmetric across the real axis there. So the other solution is negative 1/2 minus I root 3 over 2. And we'd ended by noting that these two are what are called complex conjugates of each other. And we also noticed that when you multiply complex conjugates together, you're guaranteed to get a real value as an output, because the imaginary values end up canceling each other out in the multiplication. I hope this helps. If I were going to practice this on my own, I would try and set up other simple equations. So what about solving x to the 4th minus 1 equals 0, x to the 5th minus 1 equals 0? Why does it have to be 1? Maybe you could have a different number here. So Try and make up your own StretchNet variations that just change minor parts of the problem, and then ask yourself, does this same way of thinking still apply? Does it still let you solve the original problem? Good luck.